Brenna Argall is joining us from Northwestern as we're talking to us about robots learning from motor-impaired teachers.
Thanks, Andrea, for the introduction, and thanks to the organizers for the invitation. So as Andrea mentioned, I'm from Northwestern University. I have 3 departmental affiliations there, ECS, Mechanical and Engineering, and then PM&R is Physical Medicine and Rehabilitation, so that's in the medical school. My lab is actually at the Rehabilitation Institute of Chicago, which is a hospital, a rehabilitation hospital in downtown Chicago. At RIC, we treat a variety of motor impairments and some cognitive impairments as well. We do less in the area of sensory impairments, but a little bit. And RIC has been named the #1 rehab hospital in the country for 26 consecutive years. So what that means for me as an engineering researcher, and those of us, the rest of us who are engineering researchers there, is that we have access to a really rich patient population, richer than we would see in the Chicago area naturally if we weren't pulling people from sort of around the world. And then also, we have very easy and ready access to the expertise of clinical staff and clinicians and therapists. And that really helps to sort of guide and focus our work and keep it focused on solutions that are sort of like deployable tomorrow instead of depending on technologies that might not be available for 10 years, something like that. So when I came to RIC, I was coming from a background in robotics autonomy. I had never worked in the space of assistive or rehab robotics. And what became clear, I was trying to find an intersection or a place for autonomy to sort of make an impact within this domain. So there is robotics already within the field of rehabilitation, but at least clinically, there is not higher level autonomy. So we tend to see sort of therapy machines that are replacing or augmenting what a physical therapist would already do, or we see wearable robots like exoskeletons and prostheses. So this idea of sort of higher level autonomy we don't really see clinically within rehabilitation. So in trying to come and see where there might be a place for autonomy to have impact, it became pretty clear very quickly that there are a lot of assistive machines that we see within rehabilitation that are used by people who engage in rehabilitation that are difficult for those people to operate precisely because of their motor impairments. So if we take as an example the powered wheelchair, that's by far the most ubiquitous assistive machine, and that's a 2-dimensional control problem. So you control heading and you control speed. That's very easily covered by a 2-axis joystick, and if you're able to operate a 2-axis joystick, a wheelchair very quickly becomes a natural extension of your body's own mobility. Now, if you don't have that kind of hand function, there are alternative interfaces available to you. The most common are what's called a headrest. It's switches that are embedded within the headrest of the wheelchair, so you sort of press backwards to go forwards. You'd usually do like a double tap in order to go backwards, and then you tap right and left in order to go right and left. Now, in terms of the quality of our control signal, the differences are that these are now issued in 1 dimension at a time, so you don't get a nice continuous valued 2D control signal. You get 1 dimension at a time, and it's discrete. So it's like turning a switch on and off. So you control your forward motion, or you control your turning one at a time. And if you want to go faster, you actually have to normally like sort of navigate back through this little interface. There's normally a small screen on the side of the wheelchair to navigate back through this interface in order to choose a different power level. There tend to be 4 power levels. Another common interface is the sip and puff. So if anyone's ever seen someone driving a powered wheelchair with like a straw-based interface, that's a similar sort of mechanism. Now there are sort of tricks with these interfaces to issue a 2D signal at a time, but you're actually normally kind of like latching that signal, and you're not actively controlling it anymore. It's just continuing to issue what you did before while you now issue control signals in the other dimension. So that makes wheelchair driving more difficult, but it's feasible. I mean, if you have to take a 2D control problem and sort of parse it into 1D discrete increments, it's a bit more challenging, but it's manageable. Now, if we take, for example, a robotic arm that's meant to be mounted to a powered wheelchair, these do exist commercially now. So that arm in particular is from Canova Robotics, which is a Canadian company. And to just position the end effector of a robotic arm is a 6D problem. So you have position in 3D, and you have orientation in 3D. Now, even if you're using sort of this 2-axis joystick, right, that actually only controls a fraction of this control problem. This arm is actually sold with a 3D joystick, so it additionally has twists, but that still is only half of the control space at a given time. You see that this man is actually operating the joystick with his foot. So one of the big sort of confounds or paradoxes, I would actually say, with these kind of, operating robotic arms is that if you need assistance from a robotic arm, you probably don't have the hand function to operate this kind of joystick, certainly not with twisting. And yet, those are the people who arguably need the help the most. Who would benefit the most from this sort of assistance. So we have this sort of this paradox where the more motor impaired you are, the more complex assistance you need. So maybe you need this robotic arm instead of just the wheelchair, and yet the less able you are to issue the more complex control signals that assistant or that machine requires. And so this is an opportunity for robotics autonomy. So here's an example of what those interfaces look like. So on the left, that's the head array, and on the right, that's the sip and puff. So this is an opportunity for robotics autonomy. Just to sort of recap the control challenges I was just talking about, so we have these limited interfaces that no longer span the full control space of the machine we're trying to operate and do it in a more discrete and low information content way. We have motor impairments of the person, so independent, regardless of what interface they're using, their ability to operate that interface is hampered by the fact that they have this motor impairment that's sort of filtering their true motor intent. And then we have machine complexity, that the more complex these machines get, the more complicated they are to control, and the less compatible they are with these limited control interfaces. So as I mentioned, this is an opportunity for robotics autonomy. So in particular, as we have taken robots out of factory spaces where they had very known environments and they basically had no autonomy into human environments, we've had to come up with synthetic ways to sense the world and reason about it and take action within it. And what we would like to do is leverage those approaches to help address these sensory, cognitive, and motor impairments, these gaps that are left by sensory, cognitive, and motor impairments in humans in order to assist them in operating these assistive machines. So in order to turn an assistive machine into a robot, at a high level, it's fairly straightforward. So you first need to add on sensing capabilities so that it can detect things in the environment around it, and possibly also information about the human that's operating it. Then we add on computing and artificial intelligence so that it can reason about what it sensed and also the signals that it's getting from the human. And then we've turned it into an assistive robot. Now, all of these control challenges, as I mentioned earlier, are also challenges for the autonomy as well. And we have one additional factor as well that I hadn't mentioned yet, and this is the fact that each of our users has unique and non-static abilities. So they're unique because every motor impairment is different, and also everyone has different personal preferences and how they might want to interact with autonomy. Non-static abilities is because we know that our humans are going to be changing. So it might be that they are in rehabilitation and they're regaining ability, which is what we hope for. It could be that they have a degenerative disease and they're losing ability, which is not what we hope for, but it is a reality of this domain. Or it could just be that factors like fatigue or pain throughout the day or week to week have a role in how they operate the machine and also in what kind of assistance that they would like to have. And so we need to be taking this into consideration as well. So to start out, we should be customizing this autonomy to individual users, which is a really big thing to take on. In the robotic wheelchair that we've been developing in my lab, we've prioritized two things. So one is customization for the reasons that I just mentioned, and then the other is low cost. And this is because we don't expect this is going to be covered by insurance or Medicare and Medicaid anytime soon. When a therapist fills out a form, well, when a therapist fits a person with a powered wheelchair, they actually fill out a stack of forms this thick to justify every seating cushion, every single possible decision you would make in customizing this wheelchair to that person has to be justified in order to be reimbursed by insurance. So we are not going to be reimbursed by insurance until we get onto that form. And in order to get onto that form, you need to have a lot of proof of having this kind of efficacy. So our goal, and I will consider autonomy in wheelchairs to have sort of made it when it shows up on rehabilitation form, or sorry, reimbursement forms. That you will be able to say that with these kind of motor impairments, this person would benefit from this kind of autonomy, and to get that, they need this kind of software and these kind of sensors. But that we are not expecting is going to happen anytime soon. So one way that we accomplish customization is with a modular software paradigm. So we can have any number of assistance modules that the person can sort of opt into or opt out of. We also have a modular hardware structure. Our idea is that someone comes to us with their powered wheelchair and control interface. We don't introduce custom control interfaces that might give us richer information, in part because we're not interface design experts, but also because these control interfaces have been widely vetted by the popular community or the larger community. And even if they are subpar in many different ways, they're widely vetted and they're covered by insurance. So what we want to do is do the best job that we can do in software with the kind of crappy control signals that we get from these interfaces. So the idea is that you need to add on computing power and electronics. We actually draw from the power on the wheelchair, but we have to have an inverter. And then our base system just has one RGBD sensor. Now, if we add on additional sensors, we add on robustness, we add on capabilities. It might be that some of those software modules that I introduced on the prior slide require some sort of more complex sensor. The idea is that you can get away with just one RGBD sensor and get some assistance. And then people could choose to add on additional sensors, add additional cost, but also add additional capabilities based on what their needs might be. Now, another way within software that we're accomplishing customization is in the way that we actually do control sharing. So when we have an autonomous system, of course, it's going to have an idea of what the wheelchair should do, and then the human is still issuing control signals about what they think the wheelchair should do. And how to actually reason about those two signals and create a single signal is something that is, I would argue, understudied in the field and widely variable. And it's something that needs a lot of attention in order for users to actually accept these machines. So that we've seen in a lot of different medical domains that when people feel like some sort of machine is doing too much for them or is unanticipated in how it's doing something, they just reject the technology entirely. So getting this right is going to be one of the sort of linchpins for this kind of technology.
So is that alpha value then, something the user could?
Yeah, so I'm going to be getting to that. So there's a couple of different ways to sort of customize the control sharing. So this is just a sort of simple linear blending paradigm. This is what we see a lot. Now, actually, in robotic wheelchair research, we've seen paradigms that aren't blending like this. But normally, and so there's a bunch of different ways to sort of formulate it. But then within a given formulation, of course, you can play with parameters. And that's one of the ways that we can accomplish this customization is by introducing these sort of tunable knobs. Then how to actually tune them is a big question, and I'll talk about that in a little bit. Yeah.
So is the general idea that part of the customization will occur during use?
That's what we'd like to get to eventually. Now, of course, there's a risk there that if you adapt too quickly, it becomes unanticipated and gets rejected. If you adapt too slowly, then you're not meeting their needs. And so exactly how to do that is a huge question. And actually, I'll be talking about that towards the end. We recently won a long, 5-year grant just to do that. And we're starting out by just gathering tons of teleoperation data on a robotic wheelchair and a robotic arm with people with a variety of motor impairments and people without any motor impairments to start to statistically analyze how there are differences and where, and come up with algorithms that are going to be able to appropriately adapt from that. But we're just starting that work. Okay. So the first part of my talk is going to be about sharing control between humans and assistive robots. So I just mentioned that blending is one way, this sort of blending is one way to accomplish control sharing. So I'm going to kind of sort of step through what are the different pieces of providing assistance or coming up with these autonomous systems. So in these diagrams, the green outline is the footprint of the robot. The red arrow is the control signal coming from the human user. The gray box is an obstacle, and that line at the top with the gap represents a doorway. So the first thing the autonomy needs is some kind of a goal. It can't provide any assistance if it has no idea what's going on or what the human's trying to do. So one way to do this is to actually, one way to do this is just sort of forward project into the future, like a half a second, the current control command. And this has sort of the fewest assumptions placed on what the human is trying to do. So that could be sort of like a temporary sub-goal in our system. Of course, we could also have a higher level perception system that's able to detect places where the human tends to need assistance, so spatially constrained spaces, like doorways. We have perception algorithm that is able to detect doorways just with the depth data in an RGBD camera. We also can detect docking locations at desks and at tables, and we can even anchor those locations to circular place settings, because of course there's an infinite number of places you could choose if it's all free. And for all of these, we check for clearance and safety and things like that. So of course, now if you possibly have more than one candidate location in the environment that you could go to, you have to figure out which to go to. And that's typically called intent inference within the field of robotics research. So if you watch here, my left thumb, I am teleoperating the wheelchair robot, and I'm driving it towards 2 doors. And right now my signals are ambiguous. It's not clear which doorway I want. And it's that I have to sort of give the signal a little bit to the left before it's ambiguous, or it's disambiguated. And now when I stop providing a control signal, it'll actually go through the door. So one of the first things we need to do, so first we have to be able to perceive goals in the first place. Then we need a way to sort of arbitrate between those goals. Once we've done that, we can actually come up with an autonomous signal. So here, if we now say that this is the goal we want, now we can have the autonomy come up with a safe path that reaches that goal without having any collisions. And then that gives us, at this current time step, the autonomy control signal, which is the blue arrow. So now we've got these two control signals, and we need to decide between them. So one way to decide between them is something we call filtering, but this is something we've seen in the literature come up with multiple different groups. And this is that you just cap the user's control signal to not exceed what the autonomy would have issued in either dimension in order to keep it safe. And then that would mean that we get an executed signal of that purple arrow. Yep.
So how safe or okay is it to do these extrapolations? Because maybe 9 times out of 10, if I'm heading towards the door, I do plan to actually go through the door, but maybe 1 time out of 10, I do plan to just stop before the door, maybe pick up something on the floor, or so is it always okay to extrapolate that if I'm close to the door, moving towards it, I plan to go through?
I mean, it depends how you've formulated this intent inference. So I didn't talk about it on the prior slide, but actually, for us, it's a combination of how far we are from that goal, whether or not we're sort of oriented towards it, and also whether or not the extent to which the human signal agrees with doing that. And then lots of times we have formulations where if the human stops giving a signal, it just stops. So in that case, like if the human wanted to stop and pick it up, they can. We do have formulations though where if the human stops, it's actually a cue. If we're really close to it and we're really confident that that's what they want to do, it's actually a cue that the autonomy should just take over. And again, this would be something that's customizable, that humans can choose, the user can choose what sort of paradigm they are most comfortable with.
But do you think there would be kind of are you or others also investigating, like adding any speech modality to?
So getting additional information from the human is a possibility. Like I said, we're starting from this sort of ground up, where we're trying to see what we can do so that it feels like someone is just driving the chair as they would normally drive the chair. And there's just, you can think of it kind of as like driver assist. So this is not driverless cars. This is like lane assist and collision avoidance and parking assist, things like that. I'm sure there's obviously a lot more we can do. You know, we can add in GPS, we can do all different sorts of things, but what we're trying to do is start at the base and build it up and see what gets requested and needed instead of starting the top with what robotics can do and trying to propagate it and match it to what humans might need.
And just the other direction, like could the wheelchair tell the user what that predicted goal was,
yeah.
And then they can immediately say, oh yeah, go.
Yeah. Absolutely. So that's another thing that exactly how the right way to interface that and introduce it in a way that's not too overly distracting to the human and not overly annoying, like that the robot's not constantly asking for confirmation. I think you want to do this. I think you want to do this, right? So getting that right, I think it's pretty clear that some information is going to be better than no information, but certainly there can be too much information. And so that's, I'd say, a whole nother research area. Yeah. Okay. So another way to do this control sharing is the blending paradigm that you saw earlier, the equation you saw earlier. So that was just a simple sort of linear equation. And so in this case, the purple arrow becomes sort of a mixture of these two. And we can check that the purple arrow is still going to avoid collisions, right? So here's an example actually of what that can look like. This is something that we just have running all the time actually as a safety layer underneath in the wheelchair. So again, if you watch my thumb, I'm trying to drive directly into the chair and the robot drives around it, but you see it doesn't try to like return to this position afterwards. We're not making a lot of assumptions about what the human's trying to do. We just sort of nudge them out of the way while there's a dangerous situation, and then we give them back control. And you can see that here. So this color is actually that alpha parameter we saw earlier. And so that's dictating how much control is with the human versus the robot. So when it's red, there's 0 control with the human. And when it's green, there's 100% control in the human. For computational reasons, we sort of pick increments of alpha, and we just sort of tuned this ourselves to something that felt pretty natural, but ran fast enough to run in real time on the robot. Okay, now of course we can also do this blending with our perception goal, our higher level goal, right? In which case now the purple arrow would be pushing us kind of much more to the left than it did before, because the machine is inferring that the human actually wants to try to go through the door, which in this case maybe wouldn't be the right decision based on the control signal that the human is giving. But this is just a pictorial depiction of what that might look like. And then we can do this same sort of thing at a little bit more of an aggressive way, where we just sort of do blending until we're near a sort of high-level goal, and we're really close and the human stops giving a signal, we take that as a cue, just take me through 100% autonomously, which we know that full autonomy is not a good solution for users, that it's been shown through multiple different studies, different kinds of platforms, that that's not what people want. But whether or not they occasionally want 100% autonomy, we're actually starting to see in our studies that sometimes they do, just for small, short segments of times, and when it's pretty unambiguous what it is that they're trying to do.
So, like going through the doorway, if it's narrow, I mean, it might be tricky to actually do the signaling to get it, but the computer could just...
Exactly, and I'll show some video of that actually as well, especially with these limited interfaces. It can be really hard to do these spatially constrained tasks. To get through the doorway, I think that in our wheelchair we've got about 10 centimeters clearance total, and so that's on each side. So if you're perfectly centered, that's 5 centimeters on each side, so it's pretty tight. Okay, so as I mentioned, there have been a lot of different ways to accomplish this control sharing in the literature. These are just some examples. There's other examples as well. And what we have seen is often a comparison between no autonomy, so just 100% human control, and full autonomy, or full autonomy and partial autonomy. And that's where we see that partial autonomy tends to be really, really preferred. What we haven't really seen is the fact that there's so many different ways to formulate partial autonomy, and actually a study that compares them and sees if people can actually see the difference between them or have preference between them, things like that. So that's exactly a study that we've just finished up in my lab. So in this study, we had 5 different control paradigms. So we basically had the 4 I presented on the prior slide plus full teleoperation. We had 2 different interfaces. So we had a head array, so that was where the switches are in the headrest, and we had a joystick. So we had a 1D discrete interface and a 2D continuous value interface. The study happened in 2 to 4 sessions, so we thought it would just be 2 sessions, but for some of our motor-impaired subjects, they only have a sitting tolerance of about an hour and a half. And so sometimes we had to split a given session into 2 parts for them. And we had 7 subjects with spinal cord injuries and 7 subjects without injuries. And what we were doing was a doorway traversal task. So it was a spatially constrained task. They basically went from one room in my lab through a doorway up to the second door in my lab and then out, and then my postdoc turned them around, and then we did the whole thing in reverse. So it was 4 doorway traversals in total. So here's an example of what it looks like to be just teleoperating the wheelchair with these different interfaces. So this is 0 autonomy here. On the left we have a joystick, so this is continuous valued 2D control, and on the right we have the head array. Now I should mention that this subject, while he's not necessarily familiar with our wheelchair, he has been driving a wheelchair for 25 years, and for the first 20 years after his injury, so he has a spinal cord injury, he used a head array on the right. So that is an interface that he is familiar with. And then for the last 5 years, he's been using a joystick modified with a T-bar, as you can see right there. So you can see how sort of like painstakingly slow this can be, especially using the interface on the right to try to actually align properly and go through the doorway. Yeah?
Sorry, what is the T-bar?
Oh, the T-bar is just, you see how here, he's not grasping the joystick. It's a little hard to see. It's basically that we modify it to put like a T on top of it, so you can just kind of do this if you don't have grip function. Yeah. Okay, as I mentioned, we had the 4 paradigms I talked about earlier, plus teleoperation. And here's what it looks like now with the different assistance paradigms. So I'm sure you can see a difference between using the assistance versus not, versus the videos we saw before. But you probably can't see much of a difference between the different paradigms in terms of how they're performing. And that's what we actually saw in our quantitative data as well. Well, there's not a clear winner in terms of, staying the furthest away from the doorway frame or going through the fastest, things like that. But what we do see is a very clear preference with the user among different ones. And there's actually not, well, actually, this will be easier with my next slide. So for the comparative study, these results are just a sneak peek because they're still under review, but I'll just give you a couple of high-level outputs. So one is that no single control paradigm is most preferred across subjects or performs best with statistical significance. So we asked people with each interface what was their most preferred control paradigm and least preferred, and we allowed for ties. So technically they could say I hated all of them if they wanted. At most, we normally saw 2 ties at the most. And then we asked that for each interface. Each paradigm was selected at least once, including teleoperation. Now, we did tend to see concentrations of the distribution with certain paradigms, and we did see differences between the two subject groups in terms of where that distribution sort of lay. But in general, we couldn't, there was no clear winner. There was sort of a clear loser, so we did have a statistically significant difference in preference and also in performance, where performance, in this case, I think was the number of times you had to interact with the interface, and then also the time it took to complete the task. So filtering seemed to actually sort of be a clear loser. That was the one where you cap the speeds in order to not exceed the autonomy. So I think people just kind of feel limited by that. And also because you're only ever capping and you're never augmenting, of course it performs slower. Now that didn't stop at least one person from picking it, but in general, we saw statistically significant difference.
And on an individual level, did people have sort of strong preferences?
They did. And sometimes there were ties, but they tended to have strong preferences. And I mentioned that this was a 2-session study. We also saw those preferences change between sessions. So there's definitely a familiarity, possibly learning factor happening here. And that would be a follow-on study that we need to do. Actually I have a grant in to propose that just now, to do like a 30-session study, just to see once like learning and familiarity goes away, then what do we see? Yeah.
So in statistics, these are pretty small sample sizes.
Yes.
Probably really hard to make general.
It is, and it's going to always be specific to our paradigm. What we are kind of taking away from this is not actually that this says anything about the individual paradigms, but that this is telling us that we should provide options on our chair.
Is there any way to do a bigger sort of study?
I mean, of course you can, but this is like the kind of numbers that you would want in statistics just is not practical in these kind of domains. Typically when you see like within the occupational therapy literature and stuff, it actually tends to be case studies, like one-off case studies, and maybe you've got 2 or 3. And that's sort of like that's the art of the field, just because of it's very difficult. These kind of patient populations get very sick. It's very difficult to work with, so yeah.
Sort of statistical significance aside, how do you distinguish between the control paradigms themselves and the implementation of control paradigms? Because it might be the case that, for example, especially some of the more autonomous of the control paradigms are some of the more difficult to actually implement algorithmically.
Yeah.
And it may be the case if, for example, you were able to do a Wizard of Oz-like experiment where, I don't know if that's feasible, but like some human was able to sort of see that and then
there has been one.
The intent of the patient, like at the door, and then the human could take over and do it.
So I would say, there has been one group actually in Canada that did a study like that, and that is the only other known piece of work we know that actually even tried to compare different paradigms. I would argue that the difference between a human and autonomy doing it is much greater than between different autonomy paradigms. So the human has perfect perception, has all these different sort of factors that make it very different than the autonomy. And by having all of this sort of like blips and everything that you get in autonomy, you get very, very different data. And
So then the question is, like, even if it was the case that the sample size was big enough so that you did have statistical significance, it may still not say anything about the different control paradigms because the implementations of those control paradigms might not be reflective of their ultimate potential.
So actually, these control paradigms are quite similar to each other in the sense that we are always using the same. We're computing the goal in the same way. We are computing the path in the same way. So this idea that there's a couple of parameters to tune, but not that many. And so, and in some cases, it's actually that they're sort of like iterative to each other. It's just kind of dictating how much you're taking into consideration this signal versus that signal. So while autonomy can get very complicated, because the autonomy is always at the same level. It's not that some is like super high level and some is not. The autonomy is always at the same level. And so I would say in terms of implementation, these are actually very similar in terms of their difficulty. So I understand what you're saying, and I think it's a good thing to take into consideration, but I actually don't really think it's a factor at this level of study. Okay. So another thing is that what we did see was that preference and performance both changed with control interface. So while we didn't see a clear winner, we did see both of these changing when we were using the head array versus the joystick. But we did see that these performance differences decreased with sort of increasing autonomy. So if we sort of loosely order our different control paradigms in terms of how much the autonomy is stepping in, the more autonomy that steps in, the less that we see differences in performance and preference with interface. And that's probably because the interface that's more difficult to operate, it becomes less of a factor, that difficulty, as you have more and more autonomy helping out. And we also saw performance and preference change across sessions. So this indicates that there is a human learning factor and a human familiarity factor as well. So in particular, we saw spinal cord injury subjects switch their preference about half the time when it was using the head array or the joystick. And when I say switch, I mean from session 1 to session 2, so on different days. What's sort of interesting is that we saw the same sort of rate with the head array with uninjured subjects, but we saw a much lower percentage of switch with the joystick. So this suggests that perhaps there's also an element of difficulty in this, that where for spinal cord injured subjects, there's always a certain level of difficulty because of their injury, whereas with uninjured subjects, the difficulty needs to be introduced by the interface, is one possible explanation. Okay. We also saw a few differences between subject groups, and this kind of surprised us. So in particular, we saw the greatest difference between subject groups in terms of command fluency, which was a metric we computed that basically just looked at how fluent the user's commands are. And this makes sense, right? That people with spinal cord injury, the way that they're interacting with the interface is very different. But in terms of what actually gets executed, because it's being run through our system as a whole that has autonomy helping out, we end up seeing very few differences on the whole. And the absolute fewest was actually distance to obstacles, which is sort of a safety measure. One other thing that we saw, which is another publication that's currently under review, is that we tried to look at whether or not we could model and predict people's preference based on computable metrics. Now, these computable metrics are not just metrics we typically use in robotics, so it's not just performance metrics like distance or like time, completion time. It's also a lot metrics that have to do with how the human is interacting with the machine. And that we did find that we could compute, I mean, it's pretty good. It's certainly not perfect, but that starts to give us an idea that if we wanted to be able to sort of adapt to this over time, that perhaps it is something that we would be able to do.
Did you measure, for example, how many sort of commands they had to, little interactions they had to?
We did. So that's one of the metrics that we had was number of interface interactions. And now I'm kind of grouping under performance. So when I say performance, I'm kind of making the assumption that fewer interface interactions are better. But there's also things like, you can look at the sort of like signal frequency. You can look at this fluency, things like that as well. Yeah. Okay. So going back to this slide, I've just basically showed you how we can have different formulations for how to actually like formulate the control sharing. But I haven't really talked about tuning the parameters yet, and that's what I'm going to talk about in this next study. So we explored with our robotic arm a study of end-user customization. So this is just an exploratory study. We had 4 subjects with spinal cord injuries and 13 subjects without, and they were operating our robotic arm. So we have one of those Canova arms. We have the Miko, not the Jago. And we were using this sort of linear control blending paradigm. Actually, Anka Dragan, who I believe spoke earlier this week, she had a paper where she did a literature review of these sort of control sharing or assistive paradigms. And in that literature review, she found that a lot of the paradigms actually take this functional form, roughly. So, and of course, this functional form has 3 parameters. So one is, at what point do you start providing assistance? Then how quickly do you provide it is the slope. And then at the end, when you're really confident with your ability to infer the intent of the human, actually how much control lies with the human versus autonomy. So when I'm really confident, does the human still have 30% of the control? Or do they have 0% of the control? Things like that. Now, one thing we didn't look at is that whether or not this should be anything else. So arguably, even if the robot's really confident that it knows what the human's trying to do, that doesn't necessarily mean that it should take over a lot of the control. It might be a factor of like task difficulty or other things. And one of my students, Siddhartha, is now looking into different things to have along the x-axis, but that wasn't a part of this study. So what we did in this study, I mentioned that it was exploratory. And so, of course, you can get different functional forms if you have different parameterizations. Now, we wanted people to be able to customize this function. But of course, we didn't want to just show them the function and say, change this, right? So what we did, we just had people verbally telling us how they'd like it to change. Like, I wanted the autonomy to come in sooner. And so that would mean that we should move this, right? Or I wanted the autonomy to help me out faster, which means the slope should be steeper, things like that. So this is fuzzy, but this was exploratory. Here's an example of what it looks like to be operating this robotic arm without assistance. So here he's operating it, I believe, as a 2-axis joystick. He doesn't have the hand function to twist. Now right here, when we partition the control space into these different control modes, you need a way to switch between them. As this robot is sold commercially, you switch it with a button press. Now he doesn't have the finger function to actually push a button, so he's wearing a utility cuff, and he has a pen inside of it, and that's how he's actually switching the switching the control mode. Which brings up another challenge with this sort of operational paradigm is that you actually need to remember what control mode. So you see here he switched it and actually wasn't in the control mode that he thought it would be. So you need to remember what control mode, not just what you're currently in and what the one is you want to get to, but how many button presses it takes to get there and maybe not overshooting. So then he finally gets to the control mode he wanted, and he's able to, he's trying to get the spoon into the bowl. So now here's what it looks like with assistance running. So one of the things to really note is he actually doesn't need to provide any mode switches. Now that's partly a factor of being in a control mode to start out with that's informative, right? So if I've got two objects in front of me and I'm in a control mode where I can operate along this axis, it's very informative for me to move along this axis in terms of which object I'm trying to get to. If, for example, I was in a control mode instead that did rotation, wouldn't tell me anything about which object I'm going to. And that's actually something that my student Deepak is starting to work on, is actually doing these sort of automatic mode switches in ways that help to sort of maximally inform the robotics autonomy to help disambiguate the human intent.
So,
Yeah.
so in that graph that you had with the intent on the x-axis,
Yeah. Mm-hmm.
is that some sort of probability that, or confidence?
It is, but it's not really playing a role in that. Well, yeah, no, it is. So for example, in the video I showed with the two doorways, it was a factor of the things I mentioned before, where it's the human's control signal and also the distance and heading of the robot, or distance from the goal. It's also included in that confidence is our perception confidence. So if, for example, we were only seeing the door once in every 10 frames, we wouldn't necessarily be confident that we even know that's a door in the first place, versus if we're seeing it, 9 out of 10 frames, then we're much more confident. And so that actually plays a role too. But how to actually formulate this like confidence of your intent inference also is a research area.
And so for example, in this picture over here, how many possibilities are there for what?
So there's only two. There are just these two bowls right here. And for manipulation, manipulation in the one hand is easier than the wheelchair because your workspace is limited by the size of your arm. And so if you can just perceive what's in the space of where you can actually reach, that's all you need to consider. Whereas a wheelchair can reach sort of anywhere, and so anything that's possibly in your perceptual view is an option. Now, what's harder about the robotic arm is that what you actually do once you have a goal is a lot more varied. We do a lot of different types of things with our hands and arms, whereas the wheelchair just kind of needs to drive somewhere and arrive with a certain heading and not hit things. And so it's different. The two problems are different in terms of what's more challenging.
So the confidence need not be over the ultimate goal.
It doesn't.
Just over the next correct thing to do.
Right. Which is probably actually the right thing to do. Unless you're going to have a solution that's basically autonomous and someone says, like, take me to the kitchen. If you're trying to infer, from me giving a control signal like this, whether I want to go out that door or like go down that street, there's no way to do it, and you wouldn't perform any differently in achieving those goals anyways, the sub-goals along the way. So it's generally better to just reason about the sub-goals more immediately. Yeah. Uh-huh.
Are most of these people able to speak or make noises?
They are. So these are all high spinal cord injury, but they're partial. So it's a partial spinal cord, or it was called an incomplete spinal cord injury. Otherwise, he wouldn't have any hand function. And in this case, these people, everyone we've had come to the lab has some arm and hand function, so it's not getting all the way up into the neck. But normally, even then they do, because respiration, the reason why the sip and puff is an interface is because respiration is often the last one to go. And so the last capability to go. And so they all had speech. I should clarify, they all had zero speech impairment. It wasn't just that they all could speak.
So have you tried voice command?
We have a little bit. So I've got one student who, and I don't have it in this talk, but I have a collaboration with Tom Howard at the University of Rochester, who works in speech for robots, natural language for robots. And we're starting to consider it. So of course, it could be extremely powerful. It's also much more ambiguous than like just operating an interface like this. So there's trade-offs. So I think that the right solution is probably going to be a mixture. Certainly to give a high-level goal, voice is better, right? For it to be able to say, go to the kitchen, rather than infer it from my current velocity command.
Well, voice recognition has improved over the
Right. So there actually used to be, about 20 years ago, there was a commercial voice recognition product. Well, and it was dangerous. So basically, it got trained on people just talking normally, and then when people needed to act in an emergency situation, they used a different tone of voice. So they would shout, stop, right? And it wouldn't recognize that, so it was dangerous. So while voice recognition systems are used widely like to operate computers, they don't operate physical machines. Now, obviously, voice recognition's gotten a lot better, and you can maybe ask for things like confirmation. You can maybe also do it for more like meta characteristics of the execution to say something like go faster, right? And
And you can do higher level things like go to
and do higher level things, but to issue like the lower level things to constantly say like go forward, that's probably not where you want to do it. So I think it'll probably be kind of like a partitioning.
yeah,
Yeah, yeah, exactly. We're not there yet. Yeah.
So just
Yeah.
to clarify one thing, did you say that the assistive system would actually take specific actions that would provide information to disambiguate?
That's not in this study, but that's actually something that my student Deepak, we currently have it under submission. And so we haven't done the study yet with subjects, so we've just formulated it and then done a little like pilot work. But the idea is that if you could sort of do, it's sort of like a help me help you scenario, right? Like if you are willing to operate in this control mode, I'll be able to provide you with help much earlier because I'll know what where you're trying to go. Yeah. Yeah.
I guess on the issue of voice, I mean, there's the option of the voice specifying continuous control signals similar to what a joystick does. So that it's not like they're using necessarily language or linguistic cues, but maybe paralinguistic cues or some sort of
Right.
pitch and tonality and amplitude and other sorts of things.
Right.
And then, of course, there's also BCI, brain computer interfaces, which are
Yeah.
invasive sometimes, but even if the individual doesn't have the use
Right.
of the vocal apparatus, then that's a possibility.
That is a possibility. And once we get to brain-computer interfaces that are really, really robust and really like just another commercial option, I think that'll be a game changer in these domains. I do think the tech that like getting to that point is probably, from what I've heard, it's not my area, but from what I've heard from clinicians at RIC, we're probably 15 years away. So it doesn't mean that we shouldn't be working on other stuff in the meantime. It's also different. So for operating a wheelchair, they've already shown that you can just use the sort of like skull-based EEG signals, and that's because it's just a much more discrete like control space.
Sure, but I mean, you said that, for example, specifying just the sub-goals, it might be sufficient only to get a few continuous bits, in some sense,
Yeah.
from the voice. And all you need is a microphone.
Right.
You don't need a complex apparatus to get BCI-like signals out of it.
Well, except to get, I mean, so for example, the people who've been able to operate a robotic arm with BCI are only using implantable chips.
Voice.
Okay.
Like continuous control with voice.
Right. So yeah, so sorry, so I didn't realize, I mean, I knew you had just mentioned voice, but like I didn't realize you had switched back. So I was just answering the BCI part. So it's true for voice, you could do that. One of the challenges with that is that other people can hear it, and in terms of people sort of like appearing impaired, and it's an overloaded control channel. So it's the sort of thing, I know that one of the things that therapists and people don't like about using the sip and puff is that you can't carry on a conversation when you're walking with someone else with the wheelchair, for example. So those would be considerations, but it's certainly, it's technologically feasible, I agree, absolutely. Yeah.
And maybe I missed it, just to sort of building on that. So I guess I am aware that like Drew Becknell's been doing BCI work, doing intent recognition, but also related to that, I was curious, maybe I missed it earlier, but how does the sort of type of technical approaches you're using compare to the work that say Sid at CMU's lab is doing on trying to do intent recognition? And
Yeah.
I've had some really interesting results on like people sort of sometimes reacting badly to autonomy taking over control,
Right.
And then when do you make those trade-offs?
Right. So, so at least I don't know about. So I know that some of Shervin's work, like they didn't react well. I know that in much of Sid's work, their way of like estimating intent is actually just based on distance. So I would say possibly like some of that rejection is maybe because it's not it's not taking into account enough factors, which I should say is that like something simple like distance is actually what a lot of the rest of the field was doing as well. So it might be that it just needs to be sort of more richly like formulated. I would say that, I mean, in terms of just sort of basing it on confidence and stuff like that, that's something that certainly Sid's group is doing and others in the field as well. This sort of estimate of your confidence and intent inference. So in that sense, it's very similar. But yeah, I'd say actually the fact that control sharing like diagram or model is like probably overly simplistic, and especially that what's on the x-axis is overly simplistic, I think is something that as a field we need to be working on. Yeah. All right. So So sort of some results from this exploratory study that we saw. One thing that was interesting is that the differences that we saw between spinal cord injured and subjects and uninjured. So here, the red is the spinal cord injured subjects, black is uninjured. Here we have task completion time, so we're looking at performance in that regard. And then here we have teleoperation. We have sort of a minimum amount of assistance and a maximum amount of assistance. And then custom is that what they were able to customize, and it lies somewhere in between min and max within the constraints. So one thing that was interesting is that we see that the sort of like statistically significant difference between the subject groups sort of declines with assistance type, but it still exists at max. So when we're providing as much assistance as we can, we still see statistically significant difference between these populations, but we don't once they've customized. So that kind of suggests to us that there's something else going on, and we're not entirely sure yet. This was an exploratory study, but we thought that was interesting. Another thing that was interesting was that so we had 2 phases of customization, and we saw that spinal cord injured subjects customized for more assistance, and uninjured subjects customized for less assistance. Now, of course, we only did 2 rounds, so if we did a bunch of rounds, these maybe would have sort of like normalized to sort of the same point, or like reached a steady state. But at least for this first initial just 1 round and then a second round, we saw that difference. We saw a suggestion that actually user-directed optimization was considering something more than what we normally see in sort of standard cost functions that are used within robotics. So in particular, we saw 7 of 34 customizations had a greater task completion time. So that would suggest that they were not minimizing time, which we often do in robotics objective functions. And 14 of 34 customizations have more mode switches, which would sort of relate to effort minimization, because you need to physically push that button to switch that mode. And we saw that people were not always minimizing for that either. And also when we consider the 2 of them together, we also can't explain all the data. So that suggests that there's something else going on. We don't know what it is, but something else. And then, in the interest of time, I think I am going to skip that video. Actually, we're kind of done. OK, so actually, I didn't. Yeah. So, OK, so I'm actually going to just mention one small part. So future work is adaptation. So we've kind of talked about sort of changing these adaptations over time. And when that really comes to is the actual title of my talk. So I'm going to actually skip through all of this. OK. This comes to the title of my talk, which is actually this robot learning from motor-impaired teachers and task partners. So we always have a human in the control loop, and that's an opportunity to learn from them. But of course, we have all of these challenges in learning from them that I mentioned earlier, right? The information they're giving us is filtered through their motor impairment and through the interface that they're forced to use. And we might be trying to map that information to control a more complex machine as well. So this question of what the domain of robot learning for motor-impaired teachers looks like when we have all of these challenges is a big unknown. And so in particular, if we're saying how to adapt, so this is some prior work I did during my postdoc where we actually had a tactile interface to perform adaptation for the human to give corrections to the robot. That's not going to be a viable option in this domain, most likely, because motor impairments are the reason why there's assistance. And so exactly how to perform the adaptation once we actually even have the signal is going to be a big question. So as everyone in this room knows, I mean, unless you're working in unsupervised learning domains, you need some sort of a signal, whether it's a reward signal, whether it's an example. And exactly where those signals come from is a big question. And then there's also a question of how do we actually define these in the first place? So if a human wants to actually now define something from scratch, here I'm trying to define a trajectory for a robotic arm that has 15 degrees of freedom, and there's just no interface that really does it for you. That's sort of like a standard joystick interface. So what we had to do was outfit my arm and hand with a bunch of sensors in order to get that example data. So what do examples look like in this domain of having limited interfaces and motor impairments is going to be another big question as well. And as I mentioned in the beginning of the talk, we have a big grant right now that we're going to be trying to suss this out and see if we need to develop new algorithms, or if it's just that we need to sort of reformulate of existing algorithms to expect this kind of data and perform well with this kind of data. OK, so what do you think? What? Like 5 minutes. 5 minutes? OK. So this last one that I'm going to talk about, also in the context of robot learning, is this idea of human learning as well. So actually what would be the gold standard of all of these sorts of tools is if operating the assistive device had motor learning benefits. And so this would be that So the idea would be that, someone has an injury or a disease, we do as much as we can for them in rehabilitation because we want them to regain as much of their own ability. If there's a gap then and they can't get all the way to being fully capable, we introduce assistive machines. If we introduce assistive machines with autonomy, they can help out more effectively, or at least that's the idea. What would be great is that when using that assistive machine in autonomy, you actually also can continue to help with the rehabilitation process and step the person closer to relying on that machine less or perhaps not at all. So one idea that we have within a collaborator at RIC is Sandro Musso-Valdi, and he has developed this interface. Now this is sort of an exception to what I said earlier, that we are only using commercial interfaces. His group has developed this interface called the body-machine interface, and what this is actually a vest of IMUs that's worn on the shoulders, and they take these sort of high-dimensional signals. So if you've got 4 IMUs, you get a 36-dimensional signal, and they're mapping it down to a 2D signal. And they use that to control a wheelchair or to control a 2D point on a screen. You can type on a virtual keyboard, you can play a game of Pong. And this is even for people who are quadriplegics. So people with very high spinal cord injury, if it's incomplete, you often have a very tiny bit of motion left in the shoulders. And this system can pick that up on that and actually then use it effectively. What's nice about it is that you have to move to operate the interface. So it actually potentially has rehabilitation benefits. And they currently have an R01 where they're doing a clinical trial to actually see the extent to that benefit. I would say that's also in contrast to the brain-computer interfaces, is that while this system certainly is not going to be as rich as BCI systems eventually will be, BCI systems also don't necessarily have any physical motor rehabilitation benefit. So far they've used this to operate a 2D system. What we would like to do is use it to operate a 6D system. Now, we don't even know if this is possible. Certainly when I think of how I could operate in high dimensions with my shoulders, I can think really easily of 4 dimensions. I don't know if 6 would be introducing cross terms. I don't know. And so it's unclear whether or not people are even going to be able to disambiguate that. But what our plan is to do is to have robotics autonomy help with that learning process. So the idea is that if we start out with the 6D control signal, and we have the human operating just 2 dimensions, and the robotics autonomy operating the rest, just like you saw in some of the other work in my talk, that the autonomy could be kind of monitoring the human's performance. And as the person becomes more capable, you unlock an additional control dimension. I should mention that so far Sandro's been using PCA, which on the one hand seems like an older machine learning technology, but I'd argue in this domain it's actually quite elegant, because what they do first is have someone do what they call a motion calibration dance, something like that. But they have the subjects move in all the dimensions that they can, as much as they can, and then they use that defines the variance of their mobility, right? So if now you're taking the vectors along which you have the highest variance, it makes a lot of sense from a motor learning rehabilitation standpoint. So the idea is that you can unlock an additional control dimension, and in doing that, then the human's taking over more control than the robotics autonomy. And hopefully, eventually we get to the point where maybe we don't have the autonomy, or if we do, if we can't get to that point, then the autonomy can still stay in place, and the human's at least moving to operate this machine, and perhaps regaining more control over the machine over time. And so, okay, so what we really like about this idea is that we're actually using robot machine learning in order to elicit human motor learning, hopefully. That's the idea. This is just a proof of concept that integrated the 2 systems. So this is just, the person here is just issuing a 2D control signal. One dimension is controlling the speed of the robot trajectory. The second dimension is controlling the transitions between the piecewise trajectories. So how we just transitioned here to reaching to grasping, and then grasping to carrying, and then to pouring. Each of those transitions got triggered by the body-machine interface. You'll notice that his movements are really big. That's because he has no motor impairment. And because of that body calibration dance, it's actually encouraging him to move within the full space of where he has motor capabilities. So this is just a proof of concept that the 2 systems could be integrated. And I'm going to skip all of this stuff, so sorry. Okay, so just to sort of summarize, we've talked a lot about these different kind of control challenges that we see in this domain. And the idea is that we can introduce autonomy, and the big question there is then how do you share control with the human? But then we have this additional factor where people have unique and non-static abilities. And this actually needs to play into the design of the autonomy. And once we start considering that, there's a question of how do you actually customize this to each person? And also, where do these learning signals come from once we actually start to introduce long-term adaptation over time? So that's my talk. I'd like to thank my lab members, of course, and We have a great lab space at the Rehabilitation Institute of Chicago for the next month before we move into a new hospital. But I encourage, if anyone's in Chicago, please feel welcome to stop by. Yep.
Can you say more about how you formulate that human learning objective? Like, how does the machine?
Yes, yeah. So that's certainly not my area. Sandro has expertise in that. And actually, one thing I didn't mention, one thing that the grant that we've proposed to study this actually would try to look at it. The only sort of space that we're trying to look at it in is actually how we should be unlocking the additional control dimensions. So you could imagine that you start out with the strongest control dimensions where they have the most capability, and then unlock weaker ones as they become more capable. Or you could start out with the weakest and kind of force them to work in the space that's hardest and unlock it in that direction. So that's where motor learning comes into our study. And then we'll do kind of a pilot study to sort of see what sort of range of parameters. We have a couple of different parameters in terms of how quickly we adapt the robot, and like having a slow rate of adaptation and a fast rate, just to start to see if there's differences between people. But within this initial study, we aren't going to be able to dig into it too deeply. It'll really be exploring. A lot of it'll be exploring the space. And Sandro has knows like the background field on what human motor learning looks like. I do not. Yeah.
Great. Maybe we'll take the rest of the questions during coffee break and thank Brenna.
Yeah.
So that